everyone's phone line has been muted. If you have a question, please email it to the contact information provided, and we will respond after today's webcast. Our first speaker today is Jeremy Hale and David Ward. Jeremy has over 11 years experience in the geospatial industry and is the manager for iCubed, one of the nation's leading providers of geospatial technologies. Our next speaker after that is David Ward. David has over 25 years of experience in the geospatial industry, 15 of which using various technologies to develop elevation models such as LIDAR and IFSAR technologies. Jeremy, take it away.
I'd like to thank everyone for attending today's presentation. The purpose of today's presentation is to discuss alternative technologies that might help you in either acquiring new data for a project area or enhancing your existing project data for a project that may have been completed in the past and needs to be updated. I would briefly like to go over today's agenda. First, we're going to talk about DLT Solutions a little bit, and we're going to also discuss their geospatial team. We're going to then move into a discussion on remote sensed imagery. We're going to discuss orthorectification. We're going to talk about IFSAR technology, LIDAR technology, and we're also going to talk about the Autodesk products that utilize imagery and DIM technology. DLT has worked extensively over the last several years to establish a team of technology professionals that provide their clients with access to top-tier geospatial products and services. They provide solutions and tools that optimize the life cycle of the GIS and CAD project environment. Some of their vendors include iCubed. We are one of the nation's leading suppliers of geospatial products and services. From content management, distribution, systems integration, we offer enterprise geospatial information solutions for both the commercial and government customers. GEOI is one of the nation's leading providers of remote sense data. This includes the GEOI-1 satellite, which is the highest resolution satellite commercially available in the world today. Intermap Technologies is a leading provider of DIM and IFSAR data products. Autodesk is the world's leading provider of CAD and GIS technologies. We have Google, which provides enterprise applications, and TeleAtlas, which is a leading provider of vector data. With that said, one of the first steps in any geospatial product is to acquire imagery for your project area, whether it's for preliminary design or completion, or completion of the engineering portion of your project. It's vital to have access to accurate, high-resolution imagery. Often, depending upon the project's requirements, many organizations require remotely sensed imagery from GEOI. However, before you place an order for any satellite imagery product, there are a couple of items that you need to consider. Does your project require a new collect, or can you purchase from the archive? If a new collect, what are the project timelines? One common misconception is that you can acquire an image the next day after placing an order. While we all wish this was the case, items like weather, competing projects in the region, and your project requirements all affect the collection process. The further out you can plan, the better. If it's an archive image that you're looking for, how far back can we search in the archive? GEOI has an extensive library of existing imagery dating back as far as 1999. Depending on your project requirements, this could be a suitable economic solution for acquiring imagery over a large area. Something else to consider is, does the project require the 3 bands or the multispectral band? Depending upon your project requirements, do you need to have a nice color image of for base mapping purposes, or does your project have an environmental concern that requires multispectral if you're placing an imagery order? Something else to consider is leaf on or leaf off. It's important for us to understand what you need to accomplish with your project so we can help determine what product you're looking for. If your project requires that you have the ability to see an unobstructed view of the ground, it may be important to acquire imagery that has little to no growth on the vegetation. Something else that's important to consider is explaining what you would like to do or use the imagery for. The more we can understand about the project, the better we can help find the right solution for you. And something else that kind of the purpose of our today's discussion is discussing, is accuracy important? Depending upon your project and what you need from the imagery, it can determine what type of product you're delivered. Sometimes it will also substantially affect the cost of the project. So I briefly want to kind of talk about some of the sensors that are available in the GEOI constellation. On the satellite side of the equation, they have the ORBView 2 satellite, which was launched in 1997. ORBView 2 is what we call a broad area mapping sensor. It has a 1 kilometer resolution, and it's really made for very large projects. The other sensor that they have is the ICONOS bird, and that satellite was launched in '99, and it was the first commercially available high-resolution satellite, and it's still in operation today. GEOI-1, which was launched in 2008, is currently the highest resolution commercial satellite available in the market today. In 2012, they anticipate launching GEOI-2, which again will raise the bar on the resolution. If a satellite solution is not something that you're looking for, they also have the ability to offer aerial sensors and a LIDAR sensor as well. And again, it just depends on the project requirements. Briefly, I want to kind of go over the collection capacity of GEOI and what they can collect on a given day. Both of the satellites have a tremendous capacity to collect imagery across the globe. Depending upon the sensor you're using depends upon how much data can be collected. GEOI-1 has the ability to collect up to 350,000 square kilometers a day in multispectral imagery. It can also collect 700,000 square kilometers a day in panchromatic. The ICONOS bird, which is older technology, still has the capability of collecting approximately 150,000 square kilometers a day. Something else I'd like to point out is that their constellation is in what we call a phased orbit or a sun-synchronous orbit. What that means is that they've identified that the satellite, the best sun angle for viewing and for imagery. And so they've actually locked the satellite in a sun-synchronous orbit, and it follows the sun around the Earth. Basically, it is taking an image over any given location on the globe between 10:30 and 10:45 each day. Here's an example of the extensive archive that GEOI currently has. As of January 2010, they had approximately 350 million square kilometers of imagery. And again, depending upon your project, this may be this may be a suitable alternative for acquiring imagery quickly. It's off the shelf, and it literally can be delivered to you in as little as 48 hours. So this is a good sensor that I'd like to, a comparison that I'd like to on the sensor comparison. This is, real quick, did someone hear music playing?
Reggae.
I think it's David. David, if you could mute your phone.
It's not me.
Okay, carrying on, I apologize about that. So on the sensor side, I felt this was a good slide to actually show the difference between what the ICONOS satellite is able to collect and what the GEOI-1 satellite is able to collect. If you'll notice, this is an image that was taken in the exact same location. I believe it was in New York City. And as you can see, they're both very high quality, good high quality images. However, on the GEOI-1 satellite, you're able to make out much more detail in the image. You can actually see more, and what that correlates into is the ability to extract more information for your project. Here's an example of kind of the rapid response of the sensor and its ability to collect data quickly in any location on the Earth. This image was taken April 15th in China, shortly after the earthquake. This is also an example of how this imagery can be used in emergency response scenarios. The ability to be able to provide a before and after picture can greatly enhance the responsiveness of emergency organizations. And it can show you what buildings were standing before the earthquake, which ones after, maybe where a school was, areas to concentrate your searches. Here's an example of what the Icona satellite can provide. This is the volcano that's currently going off in Iceland. This was collected on April 14th, 2010. Something that this, I think, demonstrates is the ability to actually go where aerial sensors cannot. There is no way that you could actually get a aerial platform anywhere close to this location, and yet you're able to still collect high-resolution data and know exactly what's going on in the surrounding areas. This is an example of after the earthquake in Haiti and the damage that was caused. Again, just from an emergency response standpoint, rapid response, it just highlights the ability of the satellite. Now that you've acquired your imagery, another consideration you might have is whether or not you have to have the imagery orthorectified. Depending on your project, it may not be necessary. However, if your project requires having access to highly accurate data, you will need to consider to have it orthorectified. I'd like to go over a few of the basic concepts of the orthorectification. Remotely sensed imagery such as satellites and aerial images play a vital role in general mapping, as well as GIS data acquisition and visualization for several reasons. Imagery provides a rich visual context. We are visual creatures, and often adding imagery to your project provides a level of understanding and depth previously unavailable. They provide the basis for manual and automated extraction of spatial and spectral information of our surfaces. In other words, it allows you to extract a tremendous amount of detail and information from the imagery. You can make out items such as road, you can look at vegetation, you can look at growth patterns, you can see infrastructure, you can look at land use, land cover. Literally the list is, it's got a tremendous amount of information you can acquire across the board. However, it's important to remember that the Earth is not a flat 2D surface. It is full of topographic variations. Image data acquired by airborne and satellite image sensors are affected by systematic sensor and platform-induced geometry errors, which in turn induce terrain distortions when the image sensor is not pointed directly at nadir of the location of your AOI. What that means is that if the sensor is not flying directly above your location, and if it's off to the left or the right of your center target or your target, there is going to be some distortion in the imagery. So basically, the more topographically diverse the landscape, the more distortion is going to be inherent in the photograph. So before this information can be gathered in a manner that is useful for mapping or GIS systems, the imagery must be orthorectified. This process maps one or more perspective images to their corresponding real-world locations and reduces the relief displacement caused by sensor viewing geometry and topographical relief. This is done by identifying ground truth or control points on the perspective images either manually or automatically. Ground control points can either be an accurate, something that's from accurately surveyed location or determined from existing ortho imagery. But something that needs to be for both services or both options is that it has to be a photo identifiable point. We need to be able to reference in the image that exact location. And we have to, so from a QA/QC standpoint, we have to be able to see that point. As you can notice in this lower image here, we actually have the corner of the street, which is something that can be identified. It's a known location, and we know it's not going to change. And so it just helps us verify that we're giving you an accurate product. So once a sufficient amount of ground control is collected to ensure project mapping accuracy specifications are met, the imagery can then be orthorectified using a DIM to create what's called an ortho image. Without this process, image scale would not be consistent, and you wouldn't be able to accomplish tasks such as making direct and accurate measurements of distances, angles, positions, and areas. So the Earth's topography directly affects the ortho image accuracy. High-quality DIMS coupled with accurate horizontal control creates products that can be used for a wide variety of mapping applications. In this image, you can see an example of what we're talking about. On the left-hand image, you have an image that was orthorectified using the USGS NED data. On the right-hand side, you have an image that was showed being orthorectified to the Intermaps DTM. As you can notice in the left-hand image with the NED, which is a coarser elevation set, you see some squiggles or variations in the surface there that really don't represent real world. And if you look to the right, you see a much higher accurate dim that actually can allow you to accurately represent the Earth's surface, and this can greatly impact the effectiveness of your design project. Here's another example showing, again, a before and after picture. As you can see in the center of the picture, it looks like there's some undulation in the road surface there that really isn't present. In the after picture, a lot of that is smoothed out, and you actually have a better representation of what you're seeing. So I'm going to hand the presentation over to David Ward, and he's going to discuss the LIDAR and IFSAR technologies.
Thank you, Jeremy. As you mentioned, I'm going to be briefing you on both LIDAR and IFSAR technology. I'll describe each. I'll attempt to describe where they fit in various project world, and also talk about how they can be used together in a complementary manner. Okay, interferometric synthetic aperture radar, which is a mouthful, is shortened to the acronym IFSAR. You generally will encounter it in two different forms. One is the airborne system, of which there are about a half a dozen around the world, and the other is spaceborne, and probably the product you're most familiar with is the shuttle radar product. It's about a 20-meter vertical accuracy that was done for much of the world from a shuttle mission a few years ago. There's two main products that we derive with the IFSAR technology. One is the surface model, and the other is the terrain model. And then from those, we derive a variety of different products, which I'll show you some examples of as we move through the briefing. Okay, the pros and cons of IFSAR. Let me get on the right slide here. I think the main pro for IFSAR is it's very well suited for large area coverages. Some of the flight lines we do in the collection of this data are as much as 1,400 kilometers long, so it's not a site-specific or project-specific tool, but something that needs to be considered for large area coverages. One of the nicer things about it is it can be collected at night and in virtually all weather conditions, so there's a great deal of flexibility in that. And even collecting from 38,000 feet above ground level, we're able to generate elevation models that are better than 1 meter in vertical accuracy. Now, some of the drawbacks of that is that we've got to deal with the fact that it's a single return system, so there's a little more effort involved in generating a bald earth model. And it also has some limitations in very heavily vegetated areas like rainforests or very complex urban environments like the middle of the city. So this is the kind of a summary slide about the technology. You essentially have a Learjet type aircraft with a pod on the bottom of it, and there's two antennae that are roughly 1 meter apart. So there's signals that go down simultaneously, and the phase difference in those two signals when they are recorded back at the aircraft provide a manner to derive the elevation model through a process called interferometry. This is control with GPS base stations, just like LIDAR, and there's many similarities between the two technologies that we'll point out later. Here's the two main products that are generated with IFSAR. The visual surface model on the left shows everything that is present on the surface. It's like looking down from an airplane. Here you're seeing streets and buildings and other features in a suburban area. Now, through some very intense processing, both software-driven and through a very rigorous and intense editing process, those surface features can be removed to produce a bald earth elevation model, or a DTM. So that's the main difference to appreciate between the two main products from IFSAR. So we take these two products and, using a standard specification of a 5-meter posting and a 1-meter vertical accuracy, turn those into something we call a NextMap. So IFSAR is the technology, NextMap is the product. The thing you need to appreciate. And these are very easily handled data sets. So you're looking at something in the order of 35 megabytes for either a surface model or a terrain model in an area that's the size of a 7.5 meter quad. So you don't have the huge heavy lifting involved with some very large LIDAR data sets. So this is a representation of the coverage that we currently have available. On the right-hand side, we've got 21 of the main countries in Europe that are completely covered, and the data is available from archive. And on the left-hand side is the U.S. It's a fairly major feat to get a contiguous coverage of the entire country that's to the same specification. You may be familiar with the National Elevation Data Set that USGS provides, and it's a marvelous tool, but it's made up of a series of patchwork of various data sets that are collected as much as 50 years ago in order to produce the contiguous coverage. This is all very recent data that's all done with the same process and to the same specification, so there's a dramatic difference there. This is the current status of the data that's available. Everything has been collected and it's being processed. I'm happy to report that this map is out of date, even though it's a couple weeks old. The area in Idaho is completed, and several tiles in the Indiana, Ohio, Kentucky area are completed. And we're anticipating this being totally done in the next 60 days. The small area just south of the Nevada symbol is Area 51, and that will never be available for reasons we can talk about offline. Part of the process of collecting and verifying this data, we do accuracy assessments. We're in the process of doing several around the U.S. right now, and this is one of the ones from Europe and Germany. So we've got 3,200 points that we use where we have a good visibility. They're all less than 10 degrees in slope. Excuse me, 689 points, less than 10 degrees in slope, that we then compared to our product specification. And across the board, they came out to be right in the range of 0.7 of a meter in the vertical in terms of the root mean square error. So it shows that our vertical accuracy spec is very conservative. We talk a little bit about IFSAR applications. Jeremy's already touched on one of the main ones, and that's using this very consistent, very accurate elevation model for orthorectification. But there's a number of other applications as well that should be considered. One of the more common ones is the generation of contours. You get nice, clean, easy-to-use contours from this elevation model because it's one consistent data set across the board. You don't have to worry about any discontinuity to it as you move from one type of data to the next. This is just an example of using the reflective image that comes along with the two data sets to map a very complex surface of a wind energy facility. In the lower right-hand corner, you can see the power station associated with that. Radiating to or from that are the transmission lines, and then scattered around through the site are the wind turbines and the various roads that are supporting that major facility. One of the major applications for IFSAR data is proving to be water related. The NextMap data has been accepted by the Association of Floodplain Managers for use in updating flood maps, and there's a number of active projects that are currently underway in the U.S. Watershed analysis and other types of hydrologic modeling are also applications that are very well suited to this data. This is an example of just a portion of a flood map. On your right-hand side, you can see the area along the channel with the risk assessment there. The Everything is colorized based on elevation. And then on the right-hand side, an example of flooding along a coast in terms of how that can be represented and what areas are at risk and what areas are safe based on the particular model that was run. Another of a number of other hydrologic related products that can be generated from this data. The streams, I might point out, are all contiguous, and the water all flows downhill as it should. Not the case in every data set you may run into, but it's very good for characterizing catchments, adjacent catchments, establishing drainage points, and other activities related to hydrologic modeling. In terms of some of the applications here, we've participated in providing data to do flood mapping for the entire United Kingdom that was done on a parcel-by-parcel basis, stimulated by some of the major insurance companies over there. And we currently have 9 U.S. counties that are in process developing flood mapping with the data. The data is very new, and the whole process of generating a completed flood map and getting all the certifications on it generally takes about 2 years. But we've reached an agreement with FEMA to provide this licensed data to them to archive so that they can deal with any protest to the flood mapping. So that was very necessary to enable this process. Wind farming is another very good activity that is very dependent on elevation models. Much of the site identification is done through modeling of the site with weather data. And the better quality DEM you have, the better job you can do of doing that modeling and site selection. Once you pick the sites, the data is proven to be highly useful for laying out the major features such as the transmission lines, doing the preliminary road layout, preliminary cut and fill calculations, and then you can really narrow down the area where you need to do more intense survey for the final road design. Viewshed modeling is another area where this data has proven to be very, very useful. In this case, they're looking at siting a microwave tower here and showing the neighborhoods or the land where this particular tower will be visible. And we've compared this with some of the national elevation data that's available, and we end up with a much more detailed and accurate model. We're doing topographic studies in terms of slope and aspect analysis. As you can see here, it does provide the consistency and the level of detail that makes that type of modeling very easy to accomplish. I'm going to move into LIDAR right now, which is a very similar technology. They're both active sensors. LIDAR has been around for about the last 15 years. It operates in the near-infrared part of the spectrum, and it's an interesting combination of physics, engineering, geodesy, and GIS. But this is it's kind of a summary slide that really helps you appreciate where the various components of LIDAR come from. The position of the laser is provided by the GPS. There's both a base station and a GPS unit on the aircraft, just like IFSAR. The orientation of the laser on the aircraft is provided by the inertial measurement unit. Once again, the same as with IFSAR. And then the scan angles and the ranges of the laser are provided by the sensor itself. So you assume that the speed of light is a constant, and you combine the information that's provided from items 1, 2, and 3, and you're able to generate a huge number of points, all of which have an X, Y, and Z value and an intensity value. What are the pros and cons of LIDAR in a similar type comparison that we did with IFSAR? LIDAR can be much cheaper than or less expensive than ground survey based on the size of the survey. Data collection can be accomplished in a very, very short period of time. And one of the chief advantages of LIDAR is its ability to collect information through very dense vegetation. It doesn't It doesn't pierce the vegetation itself, but a very dense pattern of points will find openings in it that enable it to get ground shots that are useful in generating the elevation model. And then the data can be classified into a number of different categories. The cons on LIDAR is it's not as cost effective on smaller sites. The deployment of a system to an area has got to be spread over a fair number of acres in order to make it a viable solution. And it is much more weather dependent than IFSAR. So in terms of kind of setting the accuracy expectations, you have ground survey being the most accurate. LIDAR is slightly less accurate than that, and IFSAR is less accurate than that in the accuracy continuum. Let's look at some example of LIDAR products that give you an idea in terms of what can be done with this data. This is a hillshade of just a highway with some agricultural areas around it, showing all the features on there. You see the cars on the highway, cars around the buildings on the area, some vegetation on the site. That can be easily removed through a combination of classification software and manual editing, much like is done with IFSAR, to end up with a very clean surface that is just what's called the bald earth surface that you're dealing with. Everything is removed. The elevation model that can be generated with good LIDAR like this can be combined with high-resolution, high-quality photography and ground control, as Jeremy has mentioned before, to produce a very good ortho. In this case, you're looking at a 10-centimeter or roughly 4-inch pixel size ortho that has very good quality to it. LIDAR data can also be used to generate contours. In this case, you see the very jaggedy contours, which, because of the point density with LIDAR, are fairly characteristic of this type of data set. It is possible to smooth them to make them more cartographically pleasing, but you also end up with a less accurate contours. Another highway example showing the level of detail possible with LIDAR. You're even seeing the tillage patterns in the agricultural field here. All the surface features there, buildings, trees, variety of things. That's just a very high level of detail. You can also shade full feature LIDAR sets by elevation as a way of doing representations of a surface. In this case, we're doing the shading by height. Clearly, the trees are the higher feature there, and it's just an interesting way of representing that surface. So how do these two technologies fit together? In a general sense, LIDAR is very, very good for complex sites such as urban environments or heavily vegetated areas. LIDAR is a tool, or excuse me, IFSAR is a tool that's best suited for less complex areas, but where you want a large coverage. So the two of them can be quite complementary. So for a county-wide project or a statewide project, it's possible to pick areas that are well suited for LIDAR, collect those with LIDAR, collect the rest of the area with IFSAR, and ended up with a blended solution that's highly useful and much more cost-effective than doing a complete project with LIDAR. A couple of side-by-side comparisons of the technologies here. IFSAR is a single return system, as I pointed out. LIDAR can be a multiple return system, or is typically a multiple return system these days. IFSAR is a side-looking sensor. LIDAR is typically done in near-nadir collection mode. IFSAR is a radar, so it's going to be a different wavelength than the near-infrared LIDAR. Once again, both active sensors, both controlled with GPS base stations and GPS on the aircraft and inertial measurement units. To give you a price comparison here, price and performance comparison on the two. The way we present IFSAR in our next map product, we're looking at a 5-meter posting for both the surface model and the terrain model. LIDAR can vary, but a fairly typical representation of that is 1-meter postings. We have a 1-meter vertical accuracy with the next map product. LIDAR is typically around 0.2 of a meter in terms of the vertical accuracy, although that can vary up somewhat and down a little bit. The cost on the next map product based on the size of the area can be anywhere from $15 to $50 a square mile. LIDAR, which is can vary from this somewhat, is around $200 per square mile, to give you kind of a rough frame of reference on both technologies. I'll give you a couple slides here showing how these how they can be blended together into one data set. So here's a sample of an IFSAR area, fairly complex scene, quite a bit of terrain. Here's the same scene showing with LIDAR. There's obviously more detail there because of the higher point density. So blending those two data sets together so they can be used without any sort of discontinuity between the two results in a product somewhat like this. And then they can be edge matched into a surface like this, where it's virtually undetectable in terms of where you move from one to the other. Once again, it's a fairly intense process of editing and quality assurance to make sure that there aren't any disconnects between the two, and they check seam lines and how it works in a visualization scenario, make sure the hydrology works well, and that the contours that are generated from that don't show any disconnection between the two different types of data. So Jeremy, I'll turn it back to you to talk about Autodesk.
Okay, thanks, Dave. So I want to go over a little bit on some of the Autodesk technology that can incorporate both the elevation model and the imagery into their product base. So Autodesk has several products that utilize both imagery and DIMS extensively. In the geospatial side, they have their AutoCAD map product, which is their base geospatial product. It has the ability to ingest imagery. You have the ability to work with it, manipulate it, export it out, send it to, convert it to different formats. They also have the raster platform, which will help in image manipulation, rubber sheeting, going in and doing just yet a higher level of orthorectification of what you need to do with the project. Another product they have is Autodesk Map Guide, which is their web-based GIS system. And all of the data that is developed in both AutoCAD Map and Raster has the ability to be exported to an Autodesk Map Guide platform to be distributed both on the intranet and in the intranet. And then another product that extensively uses imagery is their product called TopoBase, which is primarily focused on utilities and has the ability to tie into Oracle database and extract that information and publish it out. One of their products that also, or one of the directions that Autodesk is definitely kind of advancing is on the BIM side, or the Building Information Modeling. And Civil 3D, which kind of bridges both the geospatial and the BIM side of the house, has the ability to work with larger data sets. I think in the latest release of Civil 3D, or the latest service pack that came out, you have the ability to now incorporate larger DIM data sets into your work environment. And then another product is Revit. Revit is has the parametric modeling capabilities, so you not only can ingest the imagery in so you can get a feeling for what's going on outside the building, but you can also basically go from a cradle to grave operation and through the whole life cycle of your project. So here's some examples of what I was talking about. This is imagery as it's represented in each one of the platforms. At the upper left-hand corner of the screen, you're going to see imagery as it's displayed in Civil 3D. You're going to see to the right of that Map 3D, and you're going to notice that they're very similar. Civil 3D incorporates all of the functions of Core AutoCAD, Map, and their survey product. Map 3D is built upon just the core AutoCAD and has the mapping solution. The lower left-hand corner shows you an example of how imagery is displayed in the map guide and TopoBase environment. And lastly, as I was discussing the Revit and the BIM concept, you can see how imagery plays a part in the design process of your building, and you can actually see how the footprint of that building interacts with the surrounding environment. So in closing, I'd like to kind of rehash a couple things that we discussed today. DLT has developed a team of industry experts and technologies that are now at your disposal. If there's any questions, if you have any comments or thoughts on anything that was discussed today, feel free to contact us. They have an unbelievable reach, and what I refer to as their bench is quite deep. The other topic we talked about was satellite imagery. And satellite imagery is ideal for several areas. It can give you frequent revisits. So if you have a project that you're requiring multiple revisits that you have to monitor over a period of time, this is one of the areas that satellite imagery excels at. And the other is if you have to acquire imagery in a remote location. Again, you don't have the logistics costs with tasking an airplane to send it over there, getting crews out. Because the satellite is constantly passing overhead, it can hit any place on the globe. Another area that satellite imagery is really well suited for is for large project areas. Because of its large footprint, it can collect large swaths of data in one shot. And lastly, I'd like to point out the archive of existing imagery. Depending upon your project, if you can go back sometimes even a couple months, even to several years back, chances are you're going to find some imagery over your location, and it will be suitable for your project, and often is a very cost-effective way of acquiring imagery. And I'd like to rehash kind of on the LIDAR and IFSAR side. It has many advantages over conventional survey methods. And it includes you have reduced costs for large area projects. There's a rapid collection time. You have fast post-processing of the data. The turnaround is typically very quick. And when you apply that to high-resolution satellite imagery, it creates a very accurate, cost-effective product that is suitable for both CAD and GIS production. Another point I think is kind of important is with IFSAR's NextMap. This is an off-the-shelf, ready-to-use product that doesn't require any collection. It's got a very quick turnaround, and they can deliver this product very quickly for you. And this is really kind of an evolution in the industry itself, that now they're able to offer this to you. And something I'd like to bring up too about Autodesk is they are leading the charge in developing and integrating these technologies into their software solutions. They recognize the importance of these technologies and how they impact your project and your project life cycle. And they are definitely working on making sure that they get incorporated, and I'm excited to see what comes out in the next release. And the last point is to keep in mind is that the LIDAR, IFSAR, and the GOI products aren't just for new projects, but they can also enhance your existing projects. So this, if you have a project that you need to go back and you need to update, that you think needs to be reviewed, these are very economical ways to actually update that data. So I'd like to send my thank you to everyone for attending. And if you have any questions, I have some contact info up there at DLT. They will be able to get you in touch with the appropriate person. There's also their email address there. And if you send any of your questions or comments to that, it will be forwarded to the appropriate person. And lastly, you can visit them on the web at www.dlt.com. So with that said, I'm going to hand it over to Tim. Tim?
There was actually a couple questions asked, and if this presentation will be made available. And yes, this presentation was recorded, and everyone that registered will